Um, Hello everyone. In this particular video, we are going to do two things. We are going to generate some waveforms and we are going to perform some basic operations on signals. Generating waveforms, what sort of waveforms? Waveforms can be so many types, right? They can be sinusoids, they can be exponentials, they can be unit step, they can be chirps, or they can be rectangular waves. Okay, there are so many. As and when the situation arises, maybe we can tackle them. So for the time being, I'm just going to show you the generation of a sinusoidal waveform, because it's not that is sort of tricky. All other waveforms, by the way, there are no standard methods. You just know the numbers. You just have to express them. Sinusoids are sorts of tricky. Okay, so the commands, I would like you to try this. The Gaussian pulse, the pulse trend, the rectangular pulse, sawtooth, sine, sync. Okay, there are so many commands which will help you, uh, you know, generate several waveforms. But I would like you to, concentrate more on a sinusoidal waveform. Okay, so before that, let me tell you there is something called as a sampling theorem. Okay, so it says that if at all you want to generate a sinusoidal waveform, that if at all the maximum signal frequency of your sinusoidal waveform is say fm, then the sampling frequency, which is the the time instant and the discrete instant, the time instant, the gap between two time discrete time instants, one divided by the time period, should be equal to greater than twice the maximum signal frequency. Okay, keep this particular thing in mind. Okay, now suppose I want to generate a sinusoid of maximum frequency 10. Okay, it's a simple sinusoid. Frequency is 10. Okay, okay, let me go as per the instruction. Okay, let me make it 3. Then as per this particular theorem, my sampling frequency has to be more than twice the signal frequency. My signal frequency is 3, sampling frequency has to be more than the signal frequency. You can see here I'm going to go to the extreme level. Okay, I'm taking 100. How much you wanted? You wanted it to be more than 6 anyway, right? I have taken my sampling frequency as 100 so that the wave looks somewhat neat. Then you can see what is the approach here. So what I'm going to do is I will start at t. Okay, this t is to for me to substitute the value here. Wait, let me remove this particular confusion by making a comment on this particular part. Later we'll come to what that thing is. Okay, so what is the function, by the way? To generate a sine wave, you have to type in cos wave. You have to type in a cos. To generate a sine wave, you have to type a sine, SI, and I will start with the cos wave. So what is it? Cos 2 pi ft. F is the frequency of your choice, which you are given it as 3, and t is the discrete instance when you want to calculate cos 2 pi ft. So I want the values to be calculated and plotted at instance of 1 by fs. This is the time period between two discrete samples, 1 by fs. I want to start from 0 and I want to end at 1. Okay, since I give my signal frequency as 3, in a duration of 1 second, I am expecting 3 cycles. So shall we? Okay, so I'll select these lines, and only these lines I will select. Okay, then I will run the command. Okay, so there you can see in a duration from 0 to 1, I have 1, 2, and 3 cycles. Wait a second. I don't think you can see the screen. Wait a second. Okay, okay, here. Now I shared it. Now I hope you can see it. There in the figure, you can see 1, 2, and 3 cycles. There are 3 cycles. Now let us go back to the window. Okay. Now it's not so easy, by the way, to do the analysis. So what I will do is let me use the the command called as Fourier transform. Have you studied a Fourier transform? So there is this transforms. You might have studied a Z transform. You might have come across the term Laplace transforms. Then there is something called as Fourier transform. Okay, so a Laplace transform usually converts the data from time domain to S domain. Fourier is something specific. It converts the data from time domain to frequency domain. That means if at all I take the Fourier transform, I am going to know exactly the frequencies that are present. Okay, so Fourier transform usually returns a complex quantity. That is why I have to plot the absolute, that is the magnitude of it. And how many points, by the way, you can see my the original signal has 101 samples starting from 0 going till 1. So here also I will take same size, and here I have used a stem. Let me just show you this, a collective point. Okay, so here let me run this thing and let us see what has happened by going to the window. Okay, there you can see in the window, you can see 3 cycles. That is convincing that the signal has a frequency of 3. And here in the frequency domain, there is a impulse that has popped up, right? Exactly at 3. Do you see this particular impulse? X-axis here represents the frequency. Remember, in this particular signal x of t, x-axis is the time, whereas when I take the Fourier transform, my x-axis is the frequency. And you can see exactly at 3, it is showing me a stick, an impulse. This indicates that there is a frequency, there is a single frequency component 3. Wait a second. Now, who is this guy? Well, there is some mumbo jumbo about this Fourier transform. So one thing I would say, you only take, if at all there are 100 samples, you'd only see from 0 to 50. If at all my sampling frequency is 500, you only see 0 to 250. Okay. The neglect this particular second half of the Fourier transform. Concentrate only on the first half. Okay. Now let us go back. Now let us go back here. Okay. Now, what if I want to generate sum of two sinusoids? Let me do that. Let me do that here. Here you can see. Now I will generate two frequencies. One is my FM, which is this frequency. This frequency is 3. Now let me generate one more frequency. Now shall I substitute the value here only? I will take a sine wave now, and this frequency I will convert. I will choose a 6 or maybe a 7. I will choose a 7. So what I have done, you can see here, I am adding a cos wave with a sine wave. Okay, that's a possibility, right? That's an operation performed on signal. So what's going to happen? How does the signal going to look like? And what is the Fourier transform of the signal going to look like? Let us see. Yes, wait a second. Wait a second. New share. Yeah, there we're in the figure. Okay. Now you can see, now this spooky looking wave, it's actually a combination of a cos wave and a sine wave. You cannot make out anything from this particular diagram, right? But thank God there is Fourier transform. You can see, I will click this particular thing. It shows a 3, indicating one frequency component of 3 hertz. And then there is one more. Let me click this thing here. Yes, this is a second frequency component of 7 hertz. Okay. So that is how a Fourier transform is useful. Okay, in the time domain, it looks like nonsense, but in the frequency domain, if at all you watch, you can predict directly two frequencies. Okay, that was interesting. Now, wait a second. Let me, I'm coming. Yes. Okay. Hmm. Got this particular thing. Got this particular thing. Uh, here. So that was about generating a sinusoidal wave. As I told you, I am not going for any other waves quickly, but let me just show you what sort of operations you can perform on different waves. Okay, so here you can see I am doing this now, the basic operations. What all basic operations you can do? You can do some operations on the amplitude, or you can do some operations on the time. So that means operations performed on independent variable and operations performed on dependent variable. The time is an independent variable, the amplitude is the dependent variable. Now see here, let me do the amplitude scaling. So where for this cos wave, I am multiplying it by a 5. You can see a 5 star multiply. Okay, so how does that wave look like? Okay, you had seen the cos wave earlier. It's the same way, but you can see the amplitude. It's instead of a 1 being maximum, it has gone to 5. Frequency is still the same. Okay, so that is okay. I always tend to, wait a second, wait a second. Uh, One second, yeah. No, this one, okay. Sorry, just got the figures are okay, okay. Now you can see. Okay, this is what I was talking about. For a normal cos wave, the amplitude was 1 maximum, right? Cos of 90, cos 0 is equal to 1. But here you can see at origin, it is starting at 5. Okay. Now, we're done with this. Let us amplitude scaling. What else can you do? You can add two sinusoids. You can add two sinusoids. You can see here in this particular program, I have taken two sinusoids, a cos wave and a sine wave. Cos wave amplitude 5 and a sine wave of amplitude 3. Cos wave of frequency 10 and a sine wave of frequency 15. Okay, now that's the possibility. You can add it, you can amplitude scale it. Now let me just plot this particular thing and let me just show you what has popped up in going to the share. Okay, okay. There you can see some images popped up. Okay, it doesn't make any sense. By the way, this is the sum of two frequencies, 10 and sinusoids of frequencies 10 and 15. Okay, so that's there. Now, what else can you do? Just go to the program. Okay, so one thing, let me tell you, you are supposed to have a look at the workspace all the time. Okay, it is very important when you add two signals, the dimensions, the matrix dimensions must agree. Otherwise, you are going to get some, dimension mismatch error. Okay, can you subtract the sinusoids? Yes, that's a possibility. Now let me subtract the sinusoid of one is of frequency 10 and there is of frequency. Now let me not have 15. Let me have a 5 here so that the image at least looks somewhat decent. Okay, you can say a simple used a minus operator and the figure just uh, pops up. Has it? Okay, not so good, but that's the signal. What to do? Shall we take some simple frequencies? Wait a second. Let me reduce the number of frequency. Let me reduce the frequency. Okay, as I told you, my signal frequency should be much smaller than the sampling frequency. Okay, so for this demonstration sake, let me use this as 5 hertz, and this one here, let me convert it into 3 hertz. You can see this cos 2 pi ft. This phi represents the frequency. Now let me run this program once again. It's not a program. Did you observe? I am not running the complete program. These are just tiny set of instructions which we are simply running. Till now, we have not done any serious programming as such, which needs, lots and lots of commands. Okay. This one thing I just wanted to tell you. 1 second here. Wait a second. I'm just waiting for. Okay. Once. I'm just stuck. Okay. No. Okay. So there. So let me plot. Okay. So what was happening is I did not put in the sum. I put the difference here. Okay. Okay. Now we are talking. Now this one. Select it. And okay. Now has the image popped up. Wait a second. There. Yes. Now that particular wave is the difference between two sinusoids. One is of frequency 5, a cos wave, and another is of frequency 3. That's also a cos wave. Okay. So signals can be added, signals can be subtracted, signals can be scaled. Okay. What else can we do? What else can we do? Okay. So multiplication, signals can be multiplied also. Remember the famous formula cos A cos B. Cos A cos B is half cos A plus B cos A minus B. So now see there are two frequencies here. One is of frequency 15 and there is of frequency 10. Now when I added or subtracted the frequency components of the word, when I multiply, there is something strange that's going to happen. So neither the frequency 15 is going to be present, neither the frequency 10. Instead, we will get half cos A plus B and cos A minus B. So we are going to have some two new frequencies. Okay. Anyway, let us plot this. Let us multiply. So what is the command? Dot multiply. You see here the tricky things. First thing is this is signal 1, this is signal 2. I am trying to do a scalar multiplication and element by element multiplication. That is why while multiplying, I am using a dot multiply. It's not a vector multiplication. It's not a matrix multiplication. It's an array. It's a element by element multiplication. Okay. Hmm. So here, let me select these two lines and let me run this particular thing. And what has popped up? Share there. Okay. No sense. The figure does not make any sense at all. Let us go back. Let us go back and let us plot the Fourier transform. Fourier transform is, that's why we love Fourier transform. Okay. So here, what do I need to do? For Fourier transform, I better start by, defining an x-axis. Okay. I should always define an x-axis here. Okay. You see here, just as the way while plotting the time axis, you can see here for plotting the multiplication, you use time axis, define time axis. Right here we have to define the frequency axis also. Okay, okay. Control Z. Okay, control Z. One second, let me define frequency axis here. F comma. Okay, now what does this figure do? Okay, already you have one plot. Remember, already you have one plot. You do not want this Fourier transform to be plotted above it. You want it to pop up in a new window. That's why I have typed in a figure, and then I will type a plot. Okay, now let me run this particular thing. Okay, there, see, there I'm getting a error. Okay, so let me add colon to 1. This should end at 1. I think now we are fine. So matrix dimension error. Okay, the moment the matrix sizes do not agree, you are going to get into trouble. You are going to get into trouble. Wait a second. Now I'm going to show you where the image has come. A second, let me uh, here multiply. Wait a second. Evaluate selection. Now where this particular thing has come? Wait a second. Okay, so I made a change here. Okay, so there was a bug. So frequency should transform 0 to fs. Okay, so I have defined an axis. Now let me run this particular line. So I have shown you how does the multiplication look like. It was not making any sense. Now let me run this particular a Fourier transform. Okay, let me run this Fourier transform. So this particular command FFT is a command to determine the Fourier transform of the time domain signal, whatever you have given. And as I told you, since Fourier transform is a complex quantity, we can only plot the magnitude of it. We can only plot the magnitude. That is why the command ABS. ABS stands for the magnitude. Okay, the absolute values. Okay, now let me just plot this particular thing. What did I say? Cos A cos B equal to half of A plus B, A minus B. Okay, so here we are. So this is the Fourier transform. So the frequencies were 10 and 15. The sum gives you a 25. As you can see here, there's a frequency 25 because this is x-axis is frequency. There is an impulse at 25. So there is a frequency component 25, and there is a minus b, 10 minus 15, 15 minus 10, that's 5. So two new frequencies have popped up. That's what multiplication does. Okay, so that was that. What else can you do other than this? You can do the scaling. You can do the scaling. You can see. So what I've done, x of t, the time thing has been multiplied by 0.2 or a zero point 0.5. Let's keep it simple. I will take a 0.5. Now what should that do? So I have defined a new time axis here. St equal to, new time equal to time scaled by factor 0.5 t. And let us see what's going to happen. So I will use the command hold here. Before that, let me close any other commands are there. So what is this command hold do? This command hold, whenever you put hold and I put on, the graph that has been plotted already is going to stay there, and the new graph is going to be plotted above the existing graph. It helps for comparison purpose. Okay, now let us do this particular thing. This is the scaling factor. 0.5 is the scaling factor. Okay, first let us try it with 0.5, then let us try it with 2. Okay, so Let me run this to command. So what I'm doing here, first you can see xt is the original signal. Okay, xt is the original signal with frequency fm, which is how much? 3, and st is the scaled signal. St is the scaled signal where you are multiplying it by 0.5. Any guesses? How does the resulting signal going to look like? Any guesses how the resulting signal is going to look like? Let us see. Going to take you to this particular wave. One second, one second. There is a okay. Here is the signal xt, then time t. I am multiplying by 0.5. T was defined earlier. Okay, that's thing is going to be there. Now let us try and plotting them one above the other. Let us see as the image popped up once again. Okay, let me take you to the image. Okay, so you can see since you multiplied the signal by 0.5t, the signal has stretched. Okay, the signal has stretched. Okay, now what's going to happen now? Any guesses? So the blue one is the original signal x of t. The red one is the scale signal by 0.5. Now let us change the scaling factor. Let us go there. Let us change the scaling factor. How much shall I make it? Shall I make it as a 2? I'll make this as a 2. So yes, you can make your guess. Let us run and see what's going to happen now. You can make your guess. Let me run this thing and see what's going to happen now. Let me take you to okay. So scaling by a factor 0.5 actually stretch the signal. Scaling by a factor 2 has actually compressed the signal. You can see the number of cycles have doubled now. Okay, that was that. Now what else can you do? Let us see what else can you do. Then the other thing, that time shifting is over, time scaling is over, uh, multiplication. Now let us try which one? Did we do time shifting? Time shifting or not done, right? Okay, okay. Time shifting is just delay, okay? Unless there is a situation arising. Let me just show you a reflection. Let me just show you a reflection. Okay. So there is a ready command. Okay. It is called as flip from left to right. That's what I have used. So that should simulate a flip operation. Okay, I'm taking the sum t. What is the sum t? Sum t is the sum of two sinusoids which I had shown you earlier. Okay, just to have a feel of, because sinusoids were not giving me that particular feel, especially cos wave, because cos of minus theta is cos theta. It almost looks the same. Okay, now you can see, let me take you to this particular wave. You can see this blue, the signal in blue is actually sum of two sinusoids, whereas signal in red is actually its reflected version. You can see how they are mirror images of each other. Okay, towards the vertical axis. Okay, since you are watching it from 0 to 1, it's not making much sense, but since it's a sinusoid, I think you can understand what is actually going on here. Okay. So that's that. Okay, then just for sample, okay, I have plotted you a rectangular pulse. Okay, so let me do this particular command. For generating a rectangular pulse, there is a command called as rect pulse. Just as the way I told you, there can be so many, such as a Gaussian pulse, a sawtooth, right? So currently, I don't think we are much convinced. Why would you like to use something called as a Gaussian pulse? What is a Gaussian pulse or a chirp? Okay, so that's why I thought let's keep it simple. Okay, so here generating a rectangular pulse, what you can do is you can go to MATLAB and you can try a rect pulse, and hopefully document will pop up which will guide you to the entire thing. For the timing, let me show you what has just happened here. So there is a rectangular pulse that has been formed. Here you can see. Now for this particular rectangular pulse, let me just click here. It says minus 0.01, and this side there is 0.01. Okay, what is that? What is that? Let me go back. Let me go back here. Okay. Okay. So what did it say? So we defined a time period from minus zero point 0.1 to zero point 0.1. The signal is going to stay as 1, remaining all places. So the entire duration of signal is up to 20 e to the power minus 3. Out of that, that is the total width. Okay, that is the total width. Out of that, from minus zero point 0.1 to zero point 0.1, from minus zero point 0.1 to zero point 0.1 only, there was our signal. In between, there are so many discrete samples. We decided that the spacing between two samples is going to be 1 by fs. Okay, so that was that about the basic operations that can be performed on waveforms. Okay, that was about basic operations that can be performed on waveforms. Okay, thank you. Let me end this thing here.